Hello, I'm Giovanni Camurati. I will present understanding screaming channels from a detailed analysis to improve the text. Hello, I'm Giovanni Camurati. I will present understanding screaming channels. Screaming channels are a novel type of electromagnetic side channel attacks. I am a PhD student in Euricom in the south of France, and I mostly work on this, studying this interaction between radio transceivers and digital devices to see if there can be some security implications, security problems. But in general, I also like computer architectures, embedded systems, and I have been working on firmware analysis. So why are radios and computing devices together in the first place? Well, that's because modern devices are connected. So besides having computation, sensing, and actuation capabilities, they also have wireless interfaces to communicate with other devices. So for example, this device could talk with a smartphone over Bluetooth Low Energy. And to protect these communications, we need cryptographic algorithms. It's very convenient to place all these components, analog, radio frequency, digital, on the same chip because of cost reasons, area reasons, and most importantly, because it's very easy to integrate a chip with all the functionalities in one place inside a product. Unfortunately, in these cases, there can also be some issues. So let's imagine to have our device and a cryptographic algorithm, for example, AES, running on it to protect, let's say, authentication to the device. If we measure the power consumption or other physical parameters with a probe and close proximity to the device, we can extract traces which correspond to the encryptions, which are correlated with the encryptions, so that with some statistical analysis, we can find the key and break cryptography. These are called side channels, conventional side channels, but most of the time they are outside of the threat model for these kind of devices because they need physical access to the device. Instead, we have observed that the cryptographic algorithm running on the device also modulates the radio emissions, intentional radio emissions of the device. So for example, if the chip is sending Bluetooth packets, the AES algorithm modulates these packets, and the leakage is amplified and broadcast at a potentially very large distance. So that, for example, at 10 meters, we can still observe some execution traces from cryptography. We can run side channel attacks and we can break cryptography from a distance. So we call these screaming channels because the power of the leakage is high, because it's amplified by an intentional radio transmitter. So here is an example of screaming channels in practice. Let's consider this a Bluetooth low energy chip, which on the same silicon die also has a Cortex M4 processor. And let's place ourselves at 2 meters from it with a big antenna and a radio receiver. And then let's look at the radio channel. So what we can see here is a spectrogram plot. So the spectrogram plot shows the frequency on the y-axis and the time on the x-axis. So you can see the evolution of the frequency components, of the energy of the frequency components over time. And you can see that the packets for Bluetooth packets are visible. But not only that, we can also see the firmware itself executing. We can see the waiting loop, and we can see AES encryptions. In the time domain, it's maybe easier to observe them because we can recognize the characteristic key schedule and the 10 rounds of AES. So how is this possible? Well, that's because the radio transmitter is a block which uses analog radio frequency components, which are very sensitive to noise. And on the same silicon die, we also have digital blocks like the processor and memory, which use digital components, digital signals, which produce a lot of electromagnetic noise. And since the two are on the same silicon die, there are many, many possible paths for propagation. For example, the power supply, so that this noise flows from the digital part to the radio part, and it ends up modulating the radio transmission. So in general, digital activity, information about the digital activity of the chip becomes visible on the radio channel at a large distance from the device. And for example, if we look at crypto, then we can mount side channel attacks against cryptography. With this initial idea, explanation of the root cause, and a first attack in a controlled environment, but already at 10 meters, we published a first paper at CCS, and then we decided to investigate this novel leakage vector in detail to understand its peculiar characteristics, but also to improve the attacks and make them more realistic. And this paper, we just published it at CHES this year. I would like to thank all my co-authors, Marius Munk, Sebastian Pöplau, Thomas Hayes, and my supervisors, Aurélien Francillon and François-Xavier Standard. So let's now dig into screaming channels, trying to understand their characteristics more in detail. Intuitively, our victim is the CPU here on the left, on which the algorithm is running. And normally, usually in conventional side channels, we place a near field probe very close to it with a very short channel to measure its electromagnetic emissions or its power consumption and break cryptography. Instead, screaming channel traces take a completely different path. First, they flow from the CPU to the radio transmitter. And this could introduce signal-to-noise ratio changes. It could distort the signal. And then the transmitter picks up the signal, upconverts it to radio frequency, amplifies it, and broadcasts it through the antenna over the air. So now the leakage goes through a radio channel, which again could introduce signal-to-noise ratio changes or distortion. And here many more parameters can change, like the distance, the setup that we use for reception, the Bluetooth low energy channel. But most importantly, the leakage is not sent intentionally on the channel continuously. Here we have that the leakage is sent at the same time as intentional data, and the two have different or same modulation, and the packets are sent at discrete instants of time. They have a fixed length, and they don't not necessarily synchronize with the encryptions. Finally, since we're talking mostly about Bluetooth low energy in this talk, Bluetooth low energy uses frequency hopping, which means that the channel changes following a pseudo-random sequence to avoid interference. It's a form of spread spectrum. We have taken a Bluetooth low energy device and studied it in detail. I will not now focus on the methodology and on the experiments that we did that you can find in the CHES paper, but I will rather focus on the most interesting results, especially those that are useful to improve the attacks. So if we take one device, and on this very same device we run conventional side channels and screaming channels, we can observe that they have a comparable signal-to-noise ratio, even though screaming traces have a higher power and can be, let's say, extracted with a much simpler setup than the one that we need for conventional side channels with amplifiers and special probes. Both leakages are first order, but screaming channel leakages have a nonlinear distortion, which is probably introduced by the path between the digital and the radio part on the chip. So with this in mind, we find that the best attacks that we can run are profiled correlation attacks. Why? Because first, they take a profiling set of traces and they estimate the function, the leakage model between the variable that we want to discover in the cryptographic algorithm and the leakage. And this can also be a nonlinear, like it is for streaming channels. And then for an actual attack or for analysis, what we take is an attack set and we measure the linear correlation between the traces in the attack set and those in the profile. We have studied many different parameters, how the signal changes with different parameters. And we started with distance because distance is the most characteristic feature of screaming channels. However, actually distance doesn't have such a big impact on our attacks, because what really matters is the noise in the environment, the type of environment, maybe reflections or noise from other devices, and the setup. How good is the setup for a given distance? Is the antenna directional? Do we use spatial diversity, external amplifiers, and so on and so forth? So if we have a good setup adapted to the environment and the environment is not too harsh, then we can get very good correlation. Even at 10 meters, we can get even better correlation than at 10 centimeters if we use a better software-defined radio. And correlation and distortion don't change with distance, don't change with frequency, don't change with device instance. This means that the shape of the leakage, the way the chip leaks, is mostly stable and similar. And this lets us reuse profiles. This is a big advantage. Let's imagine that we want to attack a device at 10 meters in a complex environment. So what we will do is actually take a different device on which we have control. We bring it into a simple environment where there's not much noise, maybe at short distance or even via cable. We profile it, and then we reuse this profile against this other device at 10 meters that we want to attack. And this is really a big advantage of screaming channels. Once we have learned so much more about how the channel works and how to exploit it with good attacks, we looked into more challenging victims to attack. So with the CCS paper, we had some attacks via cable at 10 centimeters and even at 10 meters, but in a controlled environment. The anechoic chamber is basically protected from electromagnetic noise. So for the chest paper, we decided to make the environment more real. And we first went into a home environment with many obstacles. And we had an attack of key recovery attack at 55 centimeters. And we used the spatial diversity to take the reflections from different paths caused by the obstacles. Then we went into an office in a corridor, and we decided to push the distance at which the attack is possible. So we reached 10 meters, but this time in a realistic environment, and then even 15 meters. But I have to say that at 15 meters, the attack is really hard, in the sense that tuning the setup to these conditions is really critical. For example, tuning the direction of the directional antenna, calibrating the radio, using external amplifiers. So it took us several attempts to build a good attack set at 15 meters. What is very interesting is that we didn't even try to profile the device, the victim device, at 15 meters. We just took a different device, we built a profile via cable in a very convenient situation, and then we reused it for the attack. Interestingly, in the office, we managed to observe a leakage with a t-test at 40 meters. I mean that looking at the difference between different traces corresponding to different keys, we were able to see a signal, the presence of a leakage. And then at 60 meters, we were still able to extract AES traces in the sense of being able to observe one encryption and extract the corresponding trace. Here is an example of the attack in the office. You can see the picture just to get an idea and the number of traces that we used. And also you can observe in the scheme on the right that there were a lot of other devices and rooms and offices around. Here instead, I put a scheme of the attack at home with spatial diversity. So the idea is that the signal would take different paths, and these different paths have uncorrelated noise. So if we use more than one antenna and we pick these signals separately, then we can combine them and remove the noise and improve the signal-to-noise ratio so that an attack is still possible despite the obstacles in the middle. In general, for screaming channels, a lot of radio communication techniques can be used and leveraged to improve the attacks. We also looked into the hardware AES block. Why? Because the hardware AES block is used in many applications, including link layer encryption. Unfortunately, the hardware AES block doesn't leak as much as the CPU because it's a dedicated hardware module. So we can't see the internal computations with the key and the plain text, but we were still able to observe transfers of key, plain text, and ciphertext bytes, both in firmware, doing a mem copy, and in hardware, doing a DMA to bring the plain text and the key from one location to the peripheral. So in this case, it is possible to run some kind of side channel attacks called simple power analysis attacks, but we were not able to fully extract the plain text or the key yet. But this is a very promising direction for attacking this kind of block. So after doing attacks in a more complex environment and against a more complex target, we decided to look at real devices, a real system. And we focused on Google Eddystone beacons. What are they? They're simple devices, very small, that continuously emit some beacons, some Bluetooth low energy packets containing some information about the place or object where they are. So for example, if they are placed on a museum or sorry, on a monument, they would transmit the URL of the museum. They were really used for many applications, IoT applications and ideas like a physical web or proximity marketing, and they are still available in commerce. Since they transmit some fixed information, they need to be configured, and the owner can connect to the device and authenticate and then configure the device. So as you can see, they were designed with security and privacy in mind because telemetry data can be encrypted. The ID can be ephemeral to avoid tracking. And the authentication is protected by a good authentication protocol using AES. So let's have a look at this protocol a bit more in detail. We have a beacon, we have the owner. They both know a pre-shared key. If the owner wants to authenticate to the device, it first connects to it via Bluetooth, then reads the unlock characteristic. This is done at the, let's say, application layer. The beacon, as a response, generates a random plaintext, a random challenge P, and sends it back to the owner. Then they both compute the AES encryption with this challenge and the known pre-shared key, and the owner sends it back to the beacon by writing to the unlock characteristic. Then the beacon can compare the two ciphertexts, and if they are the same, this is the proof the owner was the right one and knew the pre-shared key, and then the owner becomes allowed to read and write more characteristics on the device. Let's now take the point of view of an attacker. The attacker can trigger AES encryptions with known random plaintext and the unknown key by simply reading the unlock characteristic. And this can be done over the air at a distance from the device. And then since we were talking about streaming channel attacks, the traces corresponding to these encryptions are visible on the radio channel over the air. So the owner can both trigger and measure AES encryptions from a distance. So this is a very interesting target for streaming channels. Unfortunately, what happens is that this is a real example in which the devices use frequency hopping. So there are 37 data channels and the frequency keeps changing and we need to follow it. So we need to have, let's say, a fast radio or enough bandwidth and know the sequence. So this is very problematic for streaming channels. But fortunately, we had the idea to use a known standard feature of the protocol to block most of the channels. This feature is the channel map, and it's available to the attacker when it connects. So now only 2 data channels are used, and the attacker can tune into one of them and mount streaming channel attacks. So the threat model is this ability to trigger and measure AES encryptions, even if the device doesn't have physical access and was not protected against side channels for this reason. We attacked a real implementation, a real demo, unmodified from the Nordic SDK with optimized code, hopping enabled, but reduced using the channel map, and AES implemented in software, the Tiny AES implementation. I want to say that the newer versions of the SDK use the hardware blocks, so as of now, they are not vulnerable to streaming channels. Our attack was in simplified conditions. We connected via cable, like we did at the beginning with the other attacks, but it already shows that a real protocol could be vulnerable to streaming channels. And when we contacted Google, we obtained a Google Bug Hunter Program honorable mention for this. If streaming channels are a problem, we need countermeasures. And we're not talking about security devices, which are have a lot of resources and are designed to be secure, like a smart card. We have devices which are very constrained in terms of cost, for example. So yes, classic countermeasures in hardware and software would work, but they are often too expensive. And it's better to look at specific countermeasures that for example, turn off the radio during sensitive computations or use the hardware block, at least for now. So without being expensive, they completely remove the channel itself. At the hardware level, we could reduce the coupling between digital part and radio, but that would be, again, expensive to design and to test. So to conclude, we have shown a generic problem, the possibility to run remote side-channel attacks from a distance because a radio broadcasts the leakage. We have seen that this leakage is peculiar. Somehow it's easier to exploit because it's amplified, but somehow it's harder to exploit because it's distorted. And we have seen more and more realistic attacks. So we need clever, specific countermeasures. We would like in the future to attack Wi-Fi and possibly the hardware block in AES. We have published our code, data, and instructions, so feel free to visit the webpage or to contact me if you want to ask questions or you want help with replicating the results of the paper. Thank you very much for coming to this talk, and I give back the scene to the organizers.